All right, welcome everyone to another BrainX community event. I'm excited to be hosting this one. My name's Dr. Chintan. I'm an intensivist in Canada with expertise in ultrasound and AI, and also part of BrainX as one of their consultants, and very passionate about education. I've been involved in medical teaching for many years, and then now obviously panning into AI as well. So we're continuing our tradition with the BrainX community Power Pack sessions. So we're gonna just I'm gonna give a little bit of a background about BrainX community, about who we are, what we do, and then we'll pass it over to our main guests of the day. So BrainX community, our main focus is to create a active and engaging environment where professionals from around the world interested in AI and medicine can come together and use machine learning to advance healthcare for the betterment of everyone. We've been active for more than 5 years and have more than 5,000 active international community members. Most of them are experts in various levels, whether in the AI field or in the medical field. And there's significant overlap and a lot of learning from each other that happens, particularly in our LinkedIn group, where we have over 2,500 members now. You can, if you want to learn more, you can visit our website at brainxai.org or brainxcommunity.com. We do have monthly BrainX community live sessions, this being one of them. But we also have many other resources available if you're whether you're starting out in the AI AI field or you're in medicine, want to transition like how I was a couple of years back, or many of us here, we're trying to make the leap. So we have a lot of resources available for people. If you go to the website, we've got an update section that gives you updates about the talks that we're going to have, our podcast, as well as up-to-date list of relevant publications in the field, which for me was a great place to start when I was first coming on here, trying to find out what's going on in the field. So many things going on. We aim to cater and filter a lot of the noise per se of many publications and papers and information coming out to create a quality repository of information that's accessible. We also help connect to different people, whether that's through our live teaching sessions and Q&As, as well as sharing that same information or through the YouTube channel. And again, the LinkedIn group would be the point where we're most active. So if you're not part of the group yet, I would invite you to join and get involved and see where you can kind of find new projects you're interested in, give feedback on ongoing projects, or just share cool news and updates in the community. We also have, if you're just looking to learn, we have a whole list of articles and other publications that might be relevant to you and for you to read, shared within the BrainX community branch of the website, as you can see here. And we've also created one of the largest repository for data sets available online, so public data sets. And we've gone through the effort of curating those and creating easy to access links here. So if you have some idea you want to test out on a data set, welcome to the website, and you're welcome to find these data sets and use how you see fit. If you have any questions or need help through that, feel free to reach out. But we also have podcast conversations with leaders in the industry like Dr. Chelly, Dr. Shetty, etc. So feel free to check those out on your free time as well. And we are a frequent face at meetings and conferences within the AI and medicine realm, and you can find up-to-date information on that on our website as well. As many of you know, the AI applications in medicine has been increasing over the last few years, and critical care especially. It's a growing field, given the sheer amount of data that we have, which we'll learn a bit more about from our other guests today. It's a prime field for revolution and significant change to our field. And I experienced this during COVID, where there's so many patients, so many data points, it's humanly impossible to keep track. And this is where machine learning and AI can really help us. And that leads to the talk for today, which is the power of causal inference. And I'm going to pass it over to the vanguards, who were actually the winners of the ESICM datathon of this year, which is an incredible accomplishment in and of itself. And the topic itself is quite interesting. So I'll hand over the mic to the vanguards and let them take over from here. Are you able to let me know if you're able to share your screen or if you have any issues with that?
Yep. Hey, Anirban here. I'm one of the members of the vanguards. Can you guys hear me okay?
Yeah, hear you loud and clear.
I'm going to start sharing our screen. So I'll kick off the presentation, but we are a team. Our team comprises of ChaoPing Wu, then Arif, Anya, Piyush, and others who couldn't make it, namely Ken. Then there's Markos, Jacob Wine, and Ronit Nath. So what is mechanical power? In the last 60, 70 years that we have been doing mechanical ventilation, we have talked about barotrauma, we have talked about volute trauma, and slowly we are realizing that there is probably a more all-encompassing metric to understand what the mechanical ventilator does. So as Gattinoni put it, it is the summation of the work done during the inflation by the ventilator during 1 minute for all inspiratory. Expiratory breath, expiratory is considered as passive, meaning that when we breathe in or inspire, that's when the ventilator delivers energy. We just want to make sure that this energy is measured over a minute of time, and that is power, basically. There are two aspects to it. One is pushing the air into the lungs, and the other aspect is expanding the lungs. Pushing the air into the lungs, or the resistive component, and expanding the lungs is the elastic component. So our hypothesis is that using sophisticated machine learning models, we can determine whether mechanical power is associated with adverse patient outcomes or not. And for this, we wanted to look at causal analysis. Why this? Because mechanical power is kind of a newer concept. Barotrauma, volute trauma, and those things have existed for a while. We wanted to come up to the mark with mechanical power because the trials are not that many. We wanted to use some of the sophisticated algorithms that we have at our disposal today. And hence, this merging of data science, this merging of mechanical ventilation to come together. We looked at process outcomes like SF ratio, PF ratio, and we looked at clinical outcomes like, what would be the length of mechanical ventilation. We purposefully stayed away from mortality because we believe that mortality is affected by many other things, and we didn't want to look at it. So we started off, like in any other causal inference study, we started off with a DAG, or a direct acyclic graph. A direct acyclic graph is basically a graph that starts off at one point or one of these nodes, which we call as the exposures. And then it travels in one direction. As complicated as it may seem, once you move away from a node, you cannot come back to that node. And then it ends up in an outcome, which in our case, as we talked, were these outcomes of SF ratio and ventilator-free days. Now, the exposures we wanted to look at specifically are aspects that go into building mechanical power. For example, the tidal volume, the PEEP, the inspiratory pressure, the respiratory rate. But there were a whole lot of other factors, like the patient's age, for example, the labs that tell us about the SOFA score of the patient. These things can also affect a patient's outcome. So we wanted to adjust for it. And then there are other variables which in our data set could not be measured, or like bilirubin, for example, or are very hard to measure, like how does the disease progress, what is the current pulmonary status, those kind of things. So we built a DAG, and the DAG has many advantages. It is a very transparent way of defining these relationships. It's a very good way for us to go back to the drawing board every time we had a question. What did we do right? What did we do wrong? And this is central to how we have approached this. With that, I'll ask ChaoPing Wu to help us or to tell us a little bit about the analysis that we have done. Over to you, ChaoPing. I'm going to stop sharing the screen.
Pink, you might be on mute. We can't hear you.
Got it. Sorry. You will imagine that after so many years, you will know how to unmute yourself. Yeah. So first I want to continue by what Anirban mentioned. In our analysis, we focus on what we know about mechanical ventilation and how mechanical ventilation can translate it to patient's outcome. So the main focus of our analysis is to tease out the causality. And causality is different than correlation. As we know right now that the most obvious example is that we all know that the rooster will crowing in the morning. Rooster crowing is correlated to the sunrise, but rooster crowing don't cause the sunrise. So correlation and causality are totally different things. We have a lot of data. We can use the observation data to tease out the correlation, but with causality, that's different things. We need a domain knowledge, and hence that what Anwar mentioned, the DAC will be very important. And how we do this kind of causality analysis? One of the way that we were using this do-why package. The special thing about this do-why package is that they actually try to identify the key causality relationship between treatment and outcome. It required a domain knowledge. And what does that mean? So as you can see over here that there's a lot of different factors we need to do in order to identify the causality. So we have the confounder variables, we have the treatment variables, and we have the outcome variables. The thing we try to tease out is how the treatment leading to the outcome with interference of the confounders. That's why that we will need to use our DAG to identify. So you can see over here, the mechanical power red dot over here, and there are two different red arrows to the ventilator free day and SF ratio. So those two pathways are the specific treatment effect that we try to identify. And we spent a lot of time to building this DAG. That's the reason why we need to know that which is the pathway actually affecting our patient and affecting the outcome. So the most important thing for this whole thing, the take home is we will need a domain knowledge. With this kind of DAG, we will be able to calculate a Bayesian network effect. So why we use do-why package? But do-why package is a very comprehensive way to evaluate the treatment effect. There are 4 different components of this package. First of all, they help us to build the model. Second thing, they'll be identify the estimate of the model. They will be able to estimate the causal effect based on the backdoor criteria or the front door criteria, use the Bayesian network. After that, one of the very important things we need to refute. What does the refute means that how valid is the estimate? You need to make sure that the estimate is not just purely by chance. You need to make sure you can do the internal validation. Similar thing when we do the supervised machine learning, we will want to do the cross validation. Okay, then finally we get a causal effect. So this is a very comprehensive process for us to comprehend that. And do-why has all of that, so which is great. And then we are going to talk about econ ML. Why there's 2 different things. Remember we talked about that in the do-why package, from the modeling to identify and to estimate and to refute. So econ ML is specific plug into the estimate phase in the phase 3. So in the prior here in the do-while package, they usually use the backdoor criterion with a linear regression. And linear regression is very suitable for the data that's randomly distributed. But we know that in the clinical setting, a lot of the variable, they will not be normally distributed. So in those kind of scenario, ECOM-ML will be very helpful because ECOM-ML was able to use the machine learning method to be able to train those data in the phase 3 over here. And also ECOM-ML has a specialty to be able to plug in most of the dynamic data, including our variable in ICU. For example, we have the hourly vital sign, hourly labs. Every of this will be able to use ECOM-ML to represent and plug to this process. All right. So what did we found in our analysis? This is the first outcome in ventilator-free day of the 28 days. So this chart looks very busy, but I'm going to guide you through what does that mean. So first of all, on the left-hand side, there are 3 different major columns. The first column is the median mechanical power and how mechanical power affecting the treatment effect. And the second column is the maximum mechanical power. And the third column is the minimum mechanical power. Just from the glance, you will see that in the first column over here, there's more things. We just say things right now. They are statistically significant. And the second row and the third row, most of them are crossing the midline, not so much significant. So just from the first glance over here, we are going to focus on median mechanical power. And what does this chart mean? So from the left-hand side, there's a very small sample over here, is the patient population. The patient population including the base meaning in the cohort across everyone. And then we separate the patient into surgery, specific surgery, cardiovascular surgery, or any kind of surgical patient, vascular surgery, to the bottom here, the respiratory failure or infection, whether the patient belongs to this cohort. So, and we kind of ranking that according to average intubation duration. So the higher over here, cardiothoracic surgeon, those kind of patient post-CABG, in general, they have shortened average intubation duration. To later on here, infection patient, respiratory failure patient, they usually have longer duration of intubation time. So, and there are 3 different charts over here. They are basically running with different kind of machine learning algorithm. The first one is just use the pure do-while linear regression. And the second one here and the third one here, they use different kind of machine learning algorithm, which we are not going to specify here. And what does that mean? That if we are looking at the base over here, it basically means that every 1 unit of increasing median mechanical power leads to 0.02 days of ventilator-free day. So it means that if you have increasing the patient mechanical power, you can cause the patient harm by reducing their ventilator-free day. So that's how we are going to interpret this chart over here. So you can find that with this knowledge in mind, looking back to this chart, you're going to find it that if the patient has relatively lower average intubation duration, they are less likely to be affected. If there's a longer duration of intubation, they are more likely to be affected. Clinically, also to us makes sense because most of the time the patient more vulnerable if they are being intubation for longer time or when they are have respiratory failure or cardiac arrest or kind of medical patient. So that's how we interpret this ventilator-free day thing. And with the do-while ECOM-ML, we can very safely say that, okay, so this treatment effect is really valid and mechanical power do lead to the worst outcome for the patients. Okay, then we talk about the second part. The second outcome we are doing right now is doing the SF ratio. And this is a very similar part with different finding. Over here, the very interesting thing we were doing is that we tried to construct a dynamic database because in the ICU, everything happened very dynamically. Every hour, patient had different setting, new labs, new inputs. So we try to construct the data based on the clinical observation. And what we try to predict that with the current ventilator setting, with the current variable in this hour, how is that going to affecting the patient SF ratio in the next 12, 24, and 36 hours. So this is just an example of one of those outcomes. And this one, you can see that there's not much significant reveal. Most of the graph over here are crossing the midline. And when we come back to think about why this that is because that probably because that we granular the detail too much, and sometimes that we lose the whole picture. And that's the reason why we kind of step back to think, how can we manipulate more of this kind of SF ratio? That's why I'm going to bring us to the next topic, which Arif is going to tell us how we do to interpret more about our outcomes. I'm going to stop sharing here.
Hello, everyone. I will start sharing my screen. Okay. As okay. So we are trying. We try to understand how the average treatment effect going on in the first 48 hours on different mechanical ventilation threshold. So in this diagram, we have three axes. One is the R, starting from admission to ICU, go up to 48 hours. And mechanical ventilation threshold means that if at that hour, a population of patients, we are comparing less than threshold against more than that threshold. So if it is 20, we divide the patient population into two, less or more than 20. And we calculated average treatment effect for each group, comparing between different groups. So in this diagram, we built 8,640 models to build these topographical kind of graphs, so 3D graphs. So in this one, we can see from every dimension what is going on, and if we are going to go higher, in order to increase the treatment effect, we should go higher value. And thanks to this 3D graphs help us to understand from every dimension. Meanwhile, we built this graph in 2 dimensions. The R against mechanical power threshold, while we can see the outcome as a PF ratio. And we didn't build only of the given illness. In this case, it is a septic shock patient. We also built in every kind of the groups. It could be medical patient, sepsis, shocks, or neuro patient. So we can from this diagram we can compare different kind of patient at the same time in different hours. Furthermore, we more interested in medical patient against surgical patient. We mostly easily divide them into 2. And in this interface, in these diagrams, we are trying to understand in every hour what is a good points, a good starting point, mechanical power at the given time. So in the beginning, the best value for both medical and the surgical patient is higher mechanical power, and when it is ongoing in the next hours, it is better to decrease the power which we are gives to the lungs. It is both good for the surgical or the medical patient. Decreasing a bit, but the value decreasing in the surgical is higher. Furthermore, in our simulation, this simulation interface, we can add noises to understand, to normalize the data. So the simulation could give us better values. And here we can compare the how is good or bad, higher noise or the worse noise. So we are trying to understand the simulation, how the simulation can continue. And we also built another interface in here in the QR code. You can go and play with our interfaces. We built all the models pre-calculated, and we built a huge database, a data set, data frame, and we can easily build a new diagram based on the selection of the on the axis and on different by using the lines and the color code, we can compare the patient. Here we can understand easily by playing with how is going on the relation between the mechanical power, the pressure, or the respiratory rate parameters, to understand, to optimize them in a better way. So we can visualize all the data on different angles, X or Y, or the color code, so the grouping by them easily and freely by the user. You can select any number to grouping them from the interface. I recommend to play with a bit the interface. It is you can easily understand the mechanical the information about the mechanical power. Here we showed the tidal volume and the mechanical power groups information. When the tidal volume is when the mechanical power is lower, the effect doesn't change based on the tidal volume or the respiratory rate. However, on the right-hand side, when the mechanical power is high, the respiratory rate is important to grouping, getting a better treatment effect. So I can give, I can stop here. Anya can continue to give her ideas about our group.
Okay. Hi, everybody. Before I begin my presentation, I'm going to give myself a short introduction so that you can better understand my perspective a little bit. My name is Anya Mathur, and I'm currently a high school student and 17 years old, which makes me the youngest on the team. And I believe that my perspective on this datathon was likely a little bit different than everyone else's, because I was truly just learning along the way. And of course, along the way, I learned a lot of new aspects of computer science and data analysis, but I also learned a lot from the team that I worked with. And I wanted to highlight the three most valuable parts of our team, which I believe were teamwork, structure, and responsibility. And so when working on a team, each of these are needed to keep everything running smoothly. And on a project this complex, where there's so many different parts and pieces and everyone has different experience with different things like coding languages, these are all very important to have. And I'm sure, as you've seen from the other speakers, the work was delegated while also maintaining trust so that everything gets done, which is absolutely vital. So the main thing that I wanted to focus on is the importance of the work that we've done. And now that you've gotten a better understanding of the work itself, as presented by the other team members, as well as how we got the work done, I wanted to start with the main question of mechanical power? What work has been done with it? Why did we choose to take a look at this? So the current exploration of mechanical power, which is MP, leaves a lot open and a lot of questions. So with the work of our team, we explore the power of mechanical power on a more insightful scale. So with the exploration that we have conducted, more can be said about mechanical power than was originally known, and we break down the importance further by looking at things like the average treatment effect, which is the 8, across different diseases. So the 8 was calculated to determine the average treatment effect for mechanical power, but we're able to break it down into more specific parts so that we can provide even more insight. Since mechanical power does not have a lot of research done, it's extremely important that when research is done, that you look at different factors so that different kinds of clinicians and people in healthcare fields can use this information, and so it has more of an impact. So we were able to consider different disease processes, different time points and thresholds, which can all contribute to the work of different clinicians today and a lot of different settings, which I think is the most important part. And along with that, even outside of the real world application, you can also look at for research. Now that we've done this sort of research, more research can be done to look into mechanical power and some other aspects that we may have not been able to look at, but have now created more of a base to start research upon. And so now I can pass it on to the next team member.
I think that's, from the presentation side. Piyush, you were part of the team. Please share, your perspective of this.
Yeah, thank you, Anirban. First of all, it was a pleasure to be on the team. And I think more than anything else, it proves to ourselves that in a short time frame, because we're just talking about a couple of months, you can take a concept, find a data set. In this case, we were provided a data set, but we are researching using other data sets too now to validate some of these models. So you can take a data set and then leverage the strengths of different team members to come up with solutions. Now, I can tell you, whether it's about causal inference model, doing it doing dynamic inference out of it, mechanical power itself, a lot of these things were very alien concepts to a lot of team members, including myself. And we were learning as we went along. So some of these are hard concepts by themselves. Each one of them, I would say, are not easy concepts by themselves. But when we work as a team and we are sharing knowledge, just like we do on BrainX community, I think it accelerates everybody's learning. And that's the beauty of these datathons and how this wonderful team from across the world came together. And that's why some of the comments that I made, that yes, we can work synchronously for certain things, but more than that, we can work a lot more asynchronously too, being mindful of time that we have at hand and the goal that we might want to achieve in a short time frame. So with all the resources that we have right now that are freely available, the open source data sets, open source models, I think the opportunity is ripe for us to turn this into meaningful applications for healthcare. So thank you, Anirban, and the team for doing such a wonderful job in just a short time frame and winning the datathon too.
Thank you, Piyush. Thank you, Anya. Thank you, Arif and Ping, for presenting this. I think we are open for questions, Chintan.
Yeah, thanks, guys. That's awesome. I mean, it's really great to hear the different perspectives. And I think this really highlights an important theme about how AI and medicine can come together. It's that people have their own lived experiences, lessons, and based on whatever journey, or whether you're a high school student or an expert already established in the field of medicine or critical care or wherever you might be. But I think this just demonstrates the most important theme is like moving together. The only way we can figure out the best possible way to integrate AI into medicine and society as a large is to actually have the different perspectives working together. So that's fantastic to see the vanguards as a group of, collective different experiences coming together to answer an important question. To that effect, there are some questions here in the chat, which I'll ask. I think the first one I saw was by Abdul Rahman, which was actually a question I had as well, which is, how was the average treatment effect calculated? And I'd add on to that is, how was it actually defined? So was that something defined by the database? Was that something you guys defined? And then the question is, how was it calculated? I'm not sure if anyone's trying to answer. Okay, there we go.
Yeah, I can take this one. So of course, we went with the standard formula for calculating average treatment effect. And, the standard formula goes something like this, that, think of Y as the outcome, X as your intervention that you did, and, let's say, ABC as other covariates, and that could be many, not just 3. So it goes like this, that, the chance of observing Y, provided you have done X, so you do the X, right? In the setting of ABC being present, right? And then there is the probability of observing Y when you don't do the X in the presence of ABC being present. Does that make sense? So you do the intervention and you don't do the intervention. And then you see what is the change in the outcome. Now, there is a trick to this, right? It is all tied up on the intervention. And, we have to find out what is the probability of getting the intervention in the first place. So you look at the chance of an outcome provided the intervention was done, and what is the probability of getting the intervention. You add 2 of them together, and you basically, that difference between those who got the intervention and those who didn't get the intervention, what was the change in the outcome? That is the average treatment effect.
Understood. And the probability of the intervention, so where do you source that number from? Do you just take the data set and whatever the incident is of that intervention, you just take that? So is it based on the data set, or do you kind of look at because different data sets will have different biases in terms of different incidents, whether based on where the critical care is, or the unit's located, what kind of population it has, et cetera, et cetera. So you just use the data set's incident, is that correct?
That is correct. So, but here's the beauty of going a DAG approach, which is the DAG is not dependent on any data set, right? It is, as being said, it is based on expert opinion, based on the, what you think you can measure in the real world.
Right.
And then you look at, you look at the data set and you look at the DAG and say, well, these I can measure. For example, in our DAG, bilirubin could not be measured because it was not captured in the database. But you look at the DAG, you look at the data set, and so think of DAG as one of the more prominent, AI scientists put it, that DAG is basically creating the estimand. By estimand, you mean it's the recipe. The data is the raw ingredients, and the average treatment effect or whatever results come out is the final product. So that's pretty much what it is. Yes, but it the DAG kind of nullifies some of the effects of the data set dependence, but it's still there.
Gotcha. That's great. Thanks for that explanation. So we have another question here from Shivani. So she's asking about how can your kind of findings be utilized to optimize mechanical ventilation settings and to reduce the ventilatory stress in critically ill patients? Does this model actually help in doing that? And how do we apply it directly to the mechanical ventilator settings and optimize them? So I guess she's questioning, how do we take the findings about MP and translate that into, I guess, any tangible practice around ventilator settings?
Sure, I can help to answer this one. So the first thing we try to identify is that whether the mechanical power truly causing certain outcomes. In our case, we try to choose, for example, ventilator-free day as one of the outcomes. So right now we know that the higher ventilation, higher mechanical power is going to lead to worse outcome, meaning less ventilator-free day. Then we know that we need to minimize the mechanical power. And the other thing that we later on doing the simulation, how much mechanical power is good, how much mechanical power is bad. So that we try to kind of simulating that how much mechanical power is too much and how much is the good threshold for the mechanical power. So by doing that, we will be able to know that if you reach into certain threshold in certain population, you are bound to leading to worse patient outcome. So we were creating this kind of what if scenario. If you are the patient in this kind of cohort with all the variable that you have, if you setting this patient with current mechanical power, this number, what does the patient outcome might look like? So that's one of the things that we can use this model to do it. And the other thing is that there's a lot of causal analysis we'll be able to using similar pathway and directing different outcome. For example, we can use a similar model and creating an outcome called weaning from the ventilator. So we can creating a mechanical power, which kind of, what is the number of mechanical power leading to winning value? So that will be the other way we can utilize this kind of model to do it. So the beauty thing about the causal analysis is that we will be able to eliminating a lot of confounding variables in clinical thing that we use based on the DAC. So how can we apply this to mechanical power settings that, so we will be able to come back to see in mechanical power, there are a lot of different variables, including mechanical power, which including P pressure, which is including tidal volume, and how can we separate those? The good thing about mechanical power, they kind of incorporate all of that together already. So, and which means it's a summarizing of all the variables that we set in clinical setting. So, and one last question that they mentioned that is, so in our model, with two different outcomes we try to predict. In the first one, the mechanical free and ventilator free day, the mechanical power is calculating by the mean of the whole day setting. And with the dynamic one, we want to use that to predict in the clinical setting. So it's hourly ventilator setting. So for example, like in hour 0, we set a patient with tidal volume 450, rate of 20, and P of 10. And we use those numbers to calculate mechanical power. And hour 2, we just kind of use the hour 1 setting to do it until the patient has a new setting popping out. So we're using the patient most current data to calculate the mechanical power.
Okay, that's awesome.
Chintan, I just want to add a couple of things. So when I look at work like this, we did this in a couple of months. And I think there are always limitations to some of the modeling that we do. And we acknowledge those limitations that might be there. That might come from data set itself. There can be biasness in the data set, as we have realized. This is a Amsterdam ICU data set. It represents only one patient population. It doesn't even necessarily represent all ICU patients. So to also add to what Ping said and what Shivani was asking, how do you translate it? I think that translational aspect requires a lot more work. The translational aspect requires further validation of that, of the model itself on another data set, the further validation across different patient populations. And then there is the part of translating it for clinical use, which is a completely different science. When you get into the science of the human-computer interface aspects of it, the implementation science of it, will the clinicians accept the guidance that you're providing through this? So I think it requires a lot more work, and that's what this wonderful team is working on. But these kind of work represent some of the early stages or are the sprouts that will eventually lead to building of some of those plants and trees eventually.
Yeah, totally. And I mean, I can down the line, I can envision something like of a similar model that, just runs in the background for a new patient that gets admitted to the ICU, monitoring and calculating the mechanical power on like a minute to minute or every hour kind of basis, and then gives feedback to the treatment team, like in terms of, I guess whether it's a score or whether like ventilator-free days, in terms of how the changes that the team is making is affecting patient outcome. And so you can kind of get like in an ideal world, you'd have like an AI that kind of just like reads this and takes the models from previously learned from different database, and it just kind of keeps getting better with each patient that comes through, and you learn how you kind of manipulate the ventilator settings, the mechanical power, and then how that impacts outcome. And then it's just kind of like a guard that like just monitors that in the background. So I can definitely see in the future how it can be applied in a very positive way. But yeah, you're right. Like it's certainly something that requires much more work. So I'm glad you guys have taken the first massive steps towards that. So that's awesome to see. I think there were a couple more questions here. I think a couple people asking about any published papers with code. I think I saw Piyush paste a link to the GitHub there up above. I think if you scroll up, there's a dataset link already posted there. But if you have any other papers related to this or previous approaches you guys might have done, I think Abhishek was asking about that. So if one of you guys want to share that either in the chat or afterwards, that'd be great.
On the way,
the question was more related to, if I understand it right, from Akash about did we have a GitHub repository that can be shared? And again, there are limitations in this based on the datathon rules, what we can share and what we cannot share. But as I'll let Anirban comment on the paper.
Yeah, thanks, Piyush. So the paper is on the way. Yeah, we just wanted to make sure datathon, as you understand, it was over 5 weeks. So we were really in a time crunch situation, but we wanted to make sure that we meet the quality checks that we need for the paper and expand it to a few other data sets for obvious reasons we were discussing. One thing I wanted to add was, we purposefully stayed away from any, thresholds that we would say this is good, this is bad, or this is the end number that we think we should move towards. I think that number is going to be different. What we were focusing more on is understanding through simulations that, when is it adding too much, when is it adding too little, and that is going to change depending on the patient, depending on their comorbidities, depending on the time that they are in their illness process, and depending, what is our goal. So I think the simulations are going to be really helpful. You can play around based on what we have defined and say, is that an acceptable result to me, or do I really not care so much? And leave the decision to the physician in the situation.
Yeah, that's incredible. Again, applaud you guys. I think there are a couple of questions more in the chat, I think, that were already answered subsequently. So can open the floor for any last questions people have they want to ask. No.
Chintan, I just want to make a comment that in the past work like this, I would make a comment that don't try this at home. I think I've modified that to say, yes, you can try this at home, but working with a team together. So yes, you can try this at home and you can do it.
And yeah, that's a perfect transition. And if you're looking for a team if you don't have a team, or you're looking to create a team or want to connect with like-minded people, BrainX community serves exactly this purpose. We help connect people like-minded who want to address important questions, want to learn new skills, and become adept at answering big questions like the vanguards have done here. So you can visit brainxai.org or brainxcommunity.com. I would also advise to join the LinkedIn group if you haven't done so. That's where you can create your own team or jump on a team or network, or simply just ask good questions and just be in the loop of essentially pioneering research. And again, to reiterate, we've recorded this session, which we'll post onto the YouTube channel. We also have podcasts that we update regularly on our website. And Piyush's email is here, so feel free to reach out. And if you have any questions, but we'd love to engage with you on a broader community, either through LinkedIn or otherwise. And thanks again for attending. And if there's no other questions, then we'll adjourn the meeting there. Okay, awesome. Well, thanks everyone. Thanks everyone taking the time. Hope you have a good day. Bye-bye.